All right, today's video is focused on exponential applications. So how do we use the exponential functions that we have been learning about for the past couple weeks in real life scenarios? So the first type we're going to look at is exponential growth. So this occurs when a quantity exponentially increases over time. So that can be like a population increase, an increase in bacteria, the expansion of like a sickness that's going around, or even an investment increasing as it builds interest over time. So the formula that we use for an exponential growth problem is f of t is a times 1 plus r to the t power. And we'll talk about what each of these variables mean. So f of t is just saying a function of time because t stands for time everywhere we see it. So it's over a certain amount of time that we're going to see growth. A is always the initial amount or the starting value. So how much does our function start with? What's the initial number of people infected, the initial amount of people that live in a city, the starting amount of an investment, that's the initial amount. And then G is our growth rate. So basically how much this investment or number of people is growing over time. So we're going to look at two exponential growth examples. So we're going to use this formula for both of them. The first says the original value of an investment is $1,800. If the value has increased by 7% each year, write an exponential function to model the situation. Then find the value of the investment after 15 years. So as I was writing here, I was kind of underlining and circling some of the important information. So we know that we're using the equation f of t equals a times 1 plus r to the t power. So the first thing is that we do know our initial amount. So our initial amount is the $1,800. Okay. Now we need to find our rate. And currently our rate is written at 7%. But we don't want to write it as a percent, but we need to write it as a decimal. So we are going to, start where our decimal point would be, and we're going to move it 2 to the left. So 1, 2. So 0.07 is our rate that goes inside. So this is our initial equation without any numbers in it. So now we know that we want to know how much the investment costs or is worth after 15 years. So everywhere that I see t, I'm going to replace it with 15 because that's the amount of time. Perfect. And the nice thing is we can actually plug this whole thing into our Desmos calculator. So we're on the side of 1,800. Then in parentheses, I'm going to have 1.07. And that's to the 15th power. And since we're talking about money here, we always want to round to the nearest cent or two numbers after the decimal. So that means I'm going to have $4,966 and 26 cents after 15 years when I initially invest $1,800. We're going to look at the same thing for number 2. So in 2002, there were 972 students enrolled at Oakview High School. Since then, the number of students has increased by 1.5% each year. Write an exponential function to model the situation, then find the number of students enrolled in 2014. So we're going to start with that basic equation. the f of t equals a times 1 plus r to the t power. We know that our initial amount that we started with was 972 students. And now we just need to find the rate. So if I have 1.5%, I'm going to move my decimal place over twice, and I get 0.015%, or 0.015 to the t power. Now, to find the number of years, we need to look at the fact that we started in 2012 and went to 2014. So how many years are between 2002 and 2014? But that would be 12 years. So everywhere that I see a T, I'm going to put a 12. I can go ahead and add the two numbers in the parentheses. Then again, I can go ahead and calculate it just by typing in the whole thing. So 972 times 1.015 to the 12th power. And this time, since we're dealing with people, we want to round to the whole number because we can't have half a person or, a quarter of a person, but we need a whole person. So I'm going to round to the whole number. So 1,162 people is how many people there would be in 2014, starting with the information that we found in 2002. Okay, so those are two exponential growth examples. We have a similar situation when it's exponential decay. The only thing that changes in our formula is with our rate. Instead of adding our rate to 1, we're going to subtract our rate from 1. So A is still the initial amount. T is still time that we're measuring it over. But R, instead of being a growth rate, is now a decay rate. Okay. So let's look at what a exponential decrease scenario could be. A lot of times these are examples like the depreciation of an asset over time. So if you buy a car or a motorcycle or something, it loses value over time, and that's called depreciation. Or maybe an investment losing value, or even the population of a town decreasing over time. If it's maybe a rural area and people are moving away into the cities, that could be an exponential decay situation. So number 3 is talking about an investment of $12,000, and it's losing value at a rate of 4% each year. We want to write an exponential function to model the situation, then find the value of an investment after 9 years. Even though it doesn't say the word decay or decrease, the fact that it's losing value is what tells us it's going to be an exponential decay function instead of an exponential growth function. So still working with the same equation. This formula is actually on your Algebra 2 formula sheet. It might use some different letters. We'll look at that later. But this isn't a formula you're going to have to memorize. You're going to know it's going to be on your sheet. But if we write it every single time we do an exponential growth or decay problem, you'll probably eventually memorize it without even trying. So some things that we know initially just from looking at the problem. We know that the initial investment is $12,000. And then to find our rate, we know that it's 4% each year. So if we were to convert that to decimal form, that would be 0.04. And we know that we are wanting to model this situation after 9 years. So everywhere I see a T, I'm going to put a 9. And before I do that, I'm going to go ahead and find what is 1 minus 0.04, put 0.96, and then I can go ahead and type that into my calculator. So 12,000.96 to the 9th power. And this one, again, since we're talking about money, we're going to round to cents, or the second number after the decimal. So this is going to give us $8,310.41. Okay, so it's a lot of investment lost over just 9 years at that rate of 4% each year. All right, example number 4. Mark bought a brand new car for $35,000 in 2008. If the car depreciates, so that word depreciates is telling us decay, it's going down. If it depreciates in value approximately 8% each year, write an exponential function to model the situation, then find the value of the car in 2015. So we know it's decay, so we're going to be subtracting that rate from 1. Just by reading our question, we know that the initial value is $35,000, and then we're going to calculate our rate. So if we're at 8%, move the decimal place over twice, we get 0.08. Okay, and then we're going to find the time over which this is happening, or how many years. We're starting in 2008, and then we're going to 2015. So there are 7 years from 2008 to 2015. So our time would be 7. So everywhere that I see a T, I'm going to replace it with 7. And I can actually go ahead and calculate what is 1 minus 0.08, which is going to give us 0.92. Even though we're going down, that number in the middle should never be negative. We should never be going down more than 100%. So if you get a negative for that number in the middle, try and recalculate. Maybe you added an extra 0 somewhere. And then now we're just going to plug it in. So 35,000 times 0.92 to the 7th power. Again, since we're talking about money or a value here, we would say we're rounding to the nearest cent. So $19,524.63. Okay, so over 7 years, this car lost a pretty significant chunk, almost $16,000 in value. Okay. All right. So the next type of exponential function or application of an exponential function that we see is what's called compound interest. So this happens when interest is calculated on the principal amount and any interest that's already been earned. So typically it's when interest is calculated more than once a year, maybe twice a year, once a month, something like that. But the formula we use is A equals P times 1 plus R over N to the NT power. So some of the terminology is going to be a little different, but we're always going to be looking for that word compounded. If you see the word compounded, that's what's going to indicate that you want to use this formula. This is also a formula that's on your Algebra 2 formula sheet. So you just need to know when to use this one compared to the other one. But P is the first variable we see, and this is talking about our principal amount. So kind of like the initial amount. R is the rate. So most likely your growth rate, so how much it's being increased by. And N is the number of times compounded. It's basically the number of times a year that the interest is calculated. And then T, again, represents time. So let's look at number 5. It says, Laura deposited $12,000 into an account that earns 8% interest. How much money will she have in 5 years if the interest is compounded quarterly? So we see compounded quarterly is what tells us we need to use this specific equation. We know our principal amount, the starting amount, is $12,000. That we see right away. Oops. Then we also see our rate right away. So we can go ahead and convert that 8% into 0.08. Okay, we know that the T is going to be 5. But now we're just looking for the number of times it's compounded. So if something is compounded quarterly, that means it's compounded 4 times a year. Just like we can think about, we have 4 quarters in the school year. Even the calendar year is broken up into 4 seasons. And each of those seasons is kind of considered a quarter. So we know that we are going to have 4 as our N value. So we can plug all of this into the Desmos calculator, but we can make less mistakes if we just simplify it just a little bit. So I know 5 times 4 is 20, so I'm going to have an exponent of 20. And then I can simplify the n side. So if I do 0.08 divided by 4, that's going to be 0.02. And 0.02 and 1 is just 1.02. So now I have something a little bit simpler to type in to Desmos. So I do 12,000 times 1.02 to the 20th power. And again, we're talking about money, so we want to do to the cents. So I have $17,831.37. Okay, so whenever your interest is compounded, it means that you're going to be earning interest or earning more money at a faster rate. So if you have the choice to take an interest rate that's compounded versus one that's uncompounded, you always want to take, I would say most of the time, you're going to do the math, and the compounded one is going to benefit you more and let you earn more over the same period of time. Okay. All right, so number 6. Jack took out a 6-year loan. For $25,000 to purchase a boat at 4.5% interest. If the interest is compounded monthly, what will he have paid over the course of the loan? So let's go ahead and put in what we know. We know that the principal or the starting amount is $25,000. I don't know why I keep putting a T there. It's supposed to be a 1. We know that this is a 6-year loan, so the time is going to be 6 years. We know that it was a 4.5% interest rate. So if we do 4.5%, move the decimal over twice, it's 0.045. And compounded monthly tells us that N is going to be 12. So we're going to put 12 in place of N. Again, we're just going to simplify it one step. before we plug it into the calculator. So 6 times 72, not 72, 6 times 12 is 72. Then we have 0.45 divided by 12 is 0.0375. So 1.0375. And now we can go ahead and calculate. So 25,000 times 1.0375 to the 72nd power. That means that we have, did I type that in right? 25,000, 1.0375. That's what I missed. I forgot, look up here. I only moved my decimal over once when I typed it in. That's why my number was so big. So let's go back here. This, we do 0.045 divided by 12 like we were supposed to. And here we should have an extra 0. So 0.00375. It's like that number is way too big for a $25,000 loan. So let's recalculate. Times 1.00375 to the 72nd power. That looks better. So over the course of the loan, he's going to pay $32,732.58. Okay, so it's always good, just like I did, to look at your answer and think about, does this make sense in my situation? And it doesn't really make sense that someone who only borrowed $25,000 would be paying back over $300,000. So that's how I knew that something in my problem went wrong, and I should go back and take a look at it. So moving on to question 7. An investment account pays 3.9% interest compounded semi-annually. If $4,000 is invested in this account, what will the balance be after 12 years? So again, we're going to start our equation, put in what we know. You know, our initial amount is that $4,000 investment. We know our rate, it's 3.9%. Move our decimal over twice. So it's 0.039. Time is 12 years. And then if it's compounded semi-annually, then that would be twice a year. Annually is once a year. Semi-annually is twice a year. So N is 2. And then we can go ahead and simplify. So I'm going to do 0.039 divided by 2. 0.0195, so 1.0195 to the 24th power. Then we can type all of that in. So 4,000 times 1.0195 to the 24th power would be $6,358.48. Okay, so once you get in the hang of identifying all of the different variables that we need and plugging them in, these questions can actually be really quick since we know the formula that we're plugging into. Okay, 2 more examples here. Number 8, a savings account offers a 0.8% interest compounded bi-monthly. If Bob deposits $300 into the account, how much interest will he earn after 10 years? So we know that our initial amount is $300. The rate, so 0.8%, we're going to move our decimal over twice. It's actually going to be a really small number, 0.008. And if something's compounded bi-monthly, that means it's going to happen twice a month. So 2 times 12 months in the year means that it's going to be compounded 24 times. So over 24, and then we have 24 times 10 years is our time. So if we want to simplify, in my calculator, I'll do 0.008 divided by 24. So this is going to give us, this is what we call scientific notation. So we actually don't have to use that. We can leave it as this fraction, which might be better for us instead of moving it out of scientific notation. But we know our exponent's going to be 240. So I can still type this in. So 300 times 1 plus, and then make that into a fraction, 0.008 over 24. Put the parentheses on the outside, raise the whole thing, the 240 power. That means that over time, the total amount will be $324.98, but it's just asking, if we look back at the question, for how much interest he will earn after 10 years. So in order to find the amount of interest, we have to subtract the amount that he initially invested into the account. So he subtracted, let me actually do this in a different color so it stands out. So he initially invested $300, so we have to subtract $300, and we get that his interest amount was $24.98. So because it was such a small interest rate, even though it was compounded 24 times a year, on such a small amount, he only earned $24.98 of interest. Okay. So our last question here says, suppose you invest $750 into an account that pays 3% interest, compounded weekly. How much interest will you have earned after 20 years? So we start with our initial amount of $750. 3%. So 3%, move our decimal over twice, gives us 0.03. Compounded weekly. So think about how many weeks there are in a year. There are 52 weeks in a year, so that means it's going to be compounded 52 times. So our n is 52. And then our time is 20. Okay. So again, if we were to type this in, the 0.03 divided by 52, we'd get a really small number. So we're just going to have to be careful when we type in this whole thing to the Desmos calculator. We're just going to type it in all at once. So 750, and then in parentheses, 1 plus, add our fraction, 0.03 over 52. Close parentheses, 252 times 20. So if you're really careful, you can also type in the exponent as multiplication. You just have to make sure that the 52 and the 20 stay in the exponent. Yeah. Perfect. So here we see that he will have earned, let me make sure I type this in right before I confidently write it down. Yep, okay. So $1,366.35. But he wants to know how much interest will be earned. So if we're just looking at interest, we subtract $750 from this. So 1366.35 minus 750 would give us $616.35 of interest. So always make sure to look at the question and to see if it's asking you for the total or something about the total. So there we go. If you have any questions, you can always send an email or make a comment on the formative. Make sure to answer all of the questions that go along with this video. It will let you know if you get them right or wrong as you go. And the assignment is due at the start of next class. So make sure you hit the submit button because that's how I'll know you're done.